Hello, my name is Farhad Eliassi. I'm a master's student at University of Utah. Today, I'll be presenting on machine learning for a spread spectrum time domain reflectometry or SSTDR impedance measurement in QNDE 2021 conference. So in order to measure the impedance of a load, LCR and VNA are mostly used measurement devices in the current market. In this slide, you can see an LCR device. In an LCR device, the measurements are done by using a frequency response analyzer to transmit a small AC voltage signal at varying frequencies. Then the complex impedance is calculated from the ratio of a voltage and current. But for this device, there are two limitations. First, this device is expensive, and the second one is the device under test should be de-energized. And in this slide, you can see a VNA. A VNA is a small is similar to the LCR in which it transmits a small AC voltage and varies frequency, but it calculates the reflection and transmission coefficients at the device under test. From these coefficients and knowledge of the transmission line impedance, the complex impedance is calculated. And there are two limitations for this device too. This is expensive, and the device under test should be de-energized. SSTDR has been widely used to detect and locate electrical faults. Dr. Cynthia First is a co-founder of Livewire Innovation, which is commercializing SSTDR technology and therefore has a financial conflict of interest with this company. However, in this study, we are using SSTDR for a different goal. Our main goal here is to measure general impedance of an unknown energized load by deploying machine learning technique and SSTDR. There are two advantages here. It is way cheaper, and SSTDR can be used on a live electrical system. Actually, after reaching our goal and extract the complex impedance, it can open up a lot of applications such as modeling battery energy storage system, measuring capacitance of the solar cells, and troubleshooting active electrical systems. So what is the SSTDR? In an SSTDR system, a high-frequency electrical signal is sent down into a transmission line where it reflects off from any impedance mismatches. And then we analyze the difference between the incident signal and reflected signal to figure out what we ran into. To simulate the SSTDR signal, we need to understand how it is built in detail. First, we built a PN code, where the PN code is a pseudo-random noise signal containing +1 and -1, and then we upsample the PN code. Next, we modulate this PN code with a 48 MHz square wave. The SSTDR signal has a sampling frequency of 4 times the modulation frequency. Then this PN modulated square wave signal should be launched down through a transmission line. So as you can see in this part of the flow chart, before launching our signal, though, we need to record a copy of our incident signal. Then in the next step, after launching the SSTDR signal, we record a copy of our reflected signal, so we can cross-correlate the two of them together. And there is an important point here. Because the PN code can be made small enough to be below the noise margin of the system under test, yet it can be pulled out through this correlation. So in this short video, I'm about to show you what happens when we cross-correlate those incident signal and reflected signals. I want you to see the incident signal. There is a red dot in the center, and there is a red dot on the far left of the reflected signal. So then we need to cross-correlate those signals together. So I'm gonna play this video. So as we are time-stepping the reflected signal through our incident signal, we are building our SSTDR response shown at the bottom of this figure. This SSTDR response here is a characteristic of an open circuit. This open circuit response is unique because it's a complete reflection of our incident signal. And another one would be a short circuit response, which is a complete inverted reflection of the incident signal. What are those responses actually telling us about the SSTDR analysis? They are actually giving us the reflection coefficient. What is the reflection coefficient, or gamma? It's a ratio of impedance between the transmission line and the load. And we can see those equations here to calculate the gamma, the reflection coefficient. So in the open circuit case, the ZL is equal to infinity and the gamma is equal to 1, and in the short circuit, the gamma is equal to -1. So I'm going to highlight the open circuit and short circuit response and move on. As I mentioned, the open circuit and short circuit responses are unique because they are upper and lower bounds of our extracted ZL and reflection coefficients. It means that any reflection signature from any impedance that's between infinity and zero will lie somewhere between our characteristic open circuit and characteristic short circuit SSTR responses. So in this slide, I'm going to show you what happens when we vary the impedance values. As shown in the resistive loads SSTR responses, we have only change in amplitude by changing the R values. However, since capacitive and inductive loads are frequency dependent, so their SSTR responses include SQs. So in this slide, we are gonna see the impact of changing the capacitance and inductance values on the SSTR responses. Capacitive loads will transition from open circuit to short circuit by increasing the capacitance values, but inductive loads do behave similar to the resistive responses. Consider such a system in which we are sending out the incident signal and we are waiting for the reflected signal. Actually, we simulate this system with 15,000 different R series RL and RC loads. And after that, we can record all of the incident and reflected signal for each simulated load. So for the next step, we use the Fourier transform to get the frequency domain representation of the time domain measurements. After getting all of the information in a frequency domain, we can calculate the reflection coefficient for each load and extract the impedance by using those formulas. So this is a flow chart of the SSTDR part of the proposed method to extract the complex value of the unknown load. In the next part, we need to consider noise in the system. In the real world, we need to take measurements in an actual electrical environment where the reflected signal might be noisy. So in this study, we add a noise to the reflected signal and simulate a noisy extracted ZL to be more practical. So what is the noise? Environment is adding a sudden noise to our measurements. There are some sources which can create noise, such as environment, vibration during using the device, or measurement error in general. And for adding a noise to the system, we need to consider an index. The index here is SNR, signal to noise ratio, is defined as the ratio of the average power of a signal, the meaningful input, to the average power of the background noise or meaningless or unwanted input. So first, we calculated the reflection coefficient in the time domain. After getting all of the reflected signal and incident signal, we can calculate the reflection coefficient easily by using this formula, Vref divided by Va incident. For the noisy data, we need to add white Gaussian noise to the reflected signal, and after that, we can use the FFT to convert all of those information to the frequency domain. And after that, we can extract the impedance, the ideal ZL and noisy ZL by using this formula in a frequency domain. In the two previous steps, our method used SSTDR responses to simulate the extracted ZL in different situations as input dataset for our machine learning network. Then we need to train the machine learning network to predict complex impedance precisely. So we are using a machine learning technique to train our network. So the machine learning that are used here is based on a supervised learning, and we are using a multiple complex regression network, mostly used for finding out the relation between the variables and forecasting. So in order to train our network, we use statsmodels.api library in the Python. And after obtaining all of the SSTDR responses as our input data, we need to split those datasets into two important parts. Actually, we assign 80% of our dataset for training set and 20% for the test dataset. So in a machine learning technique, some different variables are important. So what are those different important variables? So we need to define X-train or our noisy simulated ZL as an independent variable in a machine learning technique, and we need to define a Y-train or our ideal simulated Z as our independent variable, and after that we can have our regression model and train and model, and as an output we need to obtain those model coefficients omegas and our predicted ZL. So after creating our large data set and all of our variables are defined, we need to know how does the regression model work. So our main purpose in the training process is to fit a model with coefficients omegas to minimize the residual sum of squares between the observed targets, ideal label in the dataset, and the targets predicted by the linear approximation, the predicted y, the y hat. So in order to train our model, we need to solve inner optimization problem. So in order to solve the regression model, in the model we use gradient descent to find the optimal values of model coefficients. So as you can see in the block diagram, this is all of the training data set, regression model, and all of our outputs. So in the next level, in the evaluation process, after training our network by using training dataset, all the model coefficients, omegas, are obtained. By having all of those coefficients, we can predict the ZL from any new noisy dataset. New noisy dataset can contain actual measurement or test dataset. So as you can see here, we are using a test dataset, and in the regression model, we need to multiply those coefficients by those test dataset, and after that we can predict the ZL. For evaluating the performance of the regression model, we can use this formula to calculate the error. In summary, we simulate 15,000 different loads and convert the information from time domain to the frequency domain. Then we train the regression model by using a training dataset, which comprises noisy and ideal ZLs. Now I'm gonna show the performance of the trained model with 3 different types of the load, and SNR is equal to 25 dB. The first one is a sample resistive load from test dataset. As shown, the predicted curve is close to the ideal plot in both R and X figure. Conclusively, our method can extract the complex impedance with acceptable accuracy. As depicted in the frequency response of the SSTDR response does not have much power at lower frequencies, so it will have a negative impact at this frequency range. We can obviously see that in all figures, the proposed method shows poor performance at frequency lower than 1 MHz. In this slide, we can see acceptable performance of the proposed method for RL series load. For this load, we can see poor performance at lower frequency as well as the resistive load. These results belong to the sample RC series load, and the proposed method can extract the complex value of the load as precise as 2 previous samples. In this slide, this figure is showing the prediction error in Rx plane at frequency equal to 40 MHz. We can see 3 different regions in this figure. The region A, the circle A, the trained model has the best performance with the least amount of error in this region. In region B, proposed method has a passable performance. We can call this region confidence region. However, the region outside of the B shows higher level of error. There is an important point here. The more approaching to the open circuit values, the more prediction error we can have. This red dot here in our Rx plane is pretty close to the open circuit value. This is a sample load. And now and in this slide we plot the SSTDR response of this load. We can see from this plot that this SSTDR response is pretty close to the characteristic SSTDR response of the open circuit. So in order to see the impact of changing the SNR level, we change the SNR level and report all the errors as shown here. By increasing the SNR level, which means we would have a less noisy signal, we would have a more blue colored dots in the regions A and B. As a conclusion of our recent work, we can mention some of them here. SSTDR with machine learning can be used to measure general impedance. By finding optimal value of our trained model coefficients, our accuracy would be in the acceptable range, and we can only measure impedance within the open circuit and short circuit range very well. Actually, the performance of our algorithm is really sensitive to the SNR level and shows better performance by increasing the SNR value. And thank you so much for attending at our presentation today. Feel free to ask any question now or in the future. You can find my contact information here. And also please follow us at our group website to find our recent research works. Thank you so much.